Hello, we are Team 3 presenting on our Week 1 results for the IC Engines lab. Before running the IC engine, the force transducer must be calibrated by measuring voltage values for different applied masses on the system. The torque from the applied mass is entered into the York fit with the recorded voltage. The calibration equation stems from the results of the York fit. Acceleration data was then recorded at 0.3 volts, 0.6 volts, and 0.9 volt motor voltages, and with 1 and 4 flywheels attached. The angular velocity data for the motor running at 0.9 volts and 1 flywheel is attached and then averaged to produce the graph shown. The objective of this is to find when the motor reaches steady state. Through inspection, the angular position at which steady state occurs can be determined. The angular velocity value for steady state is calculated from averaging all velocities in the steady state zone. From this point forward, the motor maintains steady state after the 3,450 degree position. Later, the data in the green zone will be used to calculate the work of friction, whereas the work of the motor is calculated using both the red and green zones. These are the governing equations that will drive all further calculations and understanding of the IC engine. The change in kinetic energy of the flywheels from rest at position A to steady state at position B is equivalent to the summation of work on the system. The summation of work on the system includes the work of the motor, the work of friction, the work of the piston, the work of air, and the discrepancy work. Our initial assumptions for week 1 start with assuming the work of the piston is considered negligible in comparison to the other works. Since the engine head is removed, the work of air is also negligible. As discussed later on, there is no work of air, so there is no work for discrepancy. These assumptions lead to the final governing equation that the change in kinetic energy from start to steady state is equal to the external work done on the system, or the work of friction minus the work of the motor. To solve for the change in kinetic energy, the moment of inertia of the system must be determined. The theoretical moment of inertia models the flywheel as a perfect cylinder and utilizes the equation shown on the right. The mass and radius of the flywheels from the lab manuals gives us our theoretical value for the moment of inertia. The experimental moment of inertia is calculated on the values that were measured in lab. These measurements will carry uncertainty values with the equipment used for measuring, as well as error associated with not accounting for the camshaft. Comparing the theoretical moment of inertia calculated from the lab manual versus the experimental measurement yields an acceptable percent error that is expected to be within the uncertainty of the measurement devices.
As mentioned before, without the work of the piston and the work of the air, the equation to find the work of the friction and the work of the motor is simplified. From the above calibration equation, the torque on the motor is determined from the collected voltage, then is segmented by 10-degree intervals, which are averaged to define the overall torque of the motor to find the work done by the motor. When the system is at steady state, the torque due to friction can be determined, which is used to find the work done by friction. The moment of inertia is also determined experimentally. This is done by recording measurements across 3 different voltages for both flywheel configurations that were put into the system. The table shows the calculated moments of inertia from the experiment, which is significantly different from the theoretical values from the experimental measurements. This is possibly due to other parts of the system moving, such as the drive shaft and shaking of the IC engine on the test stand. In addition, the theoretical model of the moment of inertia assumes that the flywheels are perfect cylinders. This is not true in practice due to the bolts holding the flywheels in place, as well as the flywheels being individual discs. These discrepancies cause the theoretical equation to be an imprecise model of the moment of inertia, which introduces error to the system. Using the friction torque data collected in the 6 experiments before, the friction model for 1 flywheel and 4 flywheels is developed. The friction model for 1 flywheel system represents a more Coulomb friction model, which assumes that the friction increases linearly with speed, whereas the four flywheel system more clearly resembles a Newtonian friction model, which assumes that the friction increases in a quadratic or exponential manner as speed increases. However, both models are built from only 3 data points, which is not a good representation of the real system. Therefore, it is not a great assumption to make the claim that one system follows a certain model, but both systems follow these models closely and will be used in further analysis. With the moments of inertia, work of friction, work of motor, and steady-state angular velocities calculated, the week 1 work kinetic energy model is complete. From the governing equations, the steady-state kinetic energy should equal the work exterior. As shown in the results, a very small error is demonstrated between the two values due to variations in frictional losses based on speed and rounding errors. However, the errors are within acceptable limits. In the coming weeks, assumptions applied to the governing equations will be stripped away to include the work of air and discrepancy work. These changes will create a more complete work kinetic energy model that will be used to find the optimal conditions for the IC engine's power generation.
Moving to week 2, a representative cycle can be produced for the evaluation of the work of air using the experimental workflow from week 1, but with the head on the IC engine. Clearly depicted by the graphs is the 4 cycles of the IC engine: intake, compression, power, and exhaust, which each represent different contribution of the work of air. One point of interest is the dip in velocity and torque between the compression stroke and power stroke, which is expected as the work of air is applied in this part of the cycle. Future analysis will include calculating the work of air for each cycle and adding them to determine the overall work of air for the IC engine and comparing it to the theoretical work of air values. Calculating the work of air is more extensive than it sounds. When the work of air is positive, the power stroke is giving the flywheel energy, so the motor is doing less. When the work of air is negative, the compression stroke needs the flywheel energy from the motor. The calculated work of air from the system, collected from the data shown on the last slide, will be compared to a theoretical work of air for the model. The difference between these values is the discrepancy work, which will be determined in week 2. This value is attributed to anything happening in the system that is not being modeled. Applying uncertainty to this discrepancy can determine the quality of the model for the system and will be a key part of the analysis for the IC engine. Some of the more important determined uncertainties are displayed here. The uncertainty from torque is derived from the uncertainties found in the calibration equation. The uncertainty from the bin is derived from uncertainty in degrees and uncertainty in the encoder and encoder count. These uncertainties help determine the effectiveness of the model and will be used in the analysis moving forward in week 2 and 3. The goal of week 1 was to determine the work done by friction and the work done by the motor. Taking that into week 2, the 4-stroke cycle of the system can be modeled and the work done by air will be determined. In addition, the uncertainty from the work of air will be used to qualify the model used in this experiment. The goal of week 3 is to determine the optimal angles for the crankshaft during the injection cycle that will cause the IC engine to produce the most power to the generator. The angles at the beginning of the cycle and the end of the cycle will be pivotal in determining and maximizing the power output of the engine. Thank you for your attention throughout this presentation.